back to calculus 1. Excuse me. This time we are moving to uh, the derivative formulas and the rules. Section 3.3, the so-called differentiation rules. I hope you still remember the definition of the derivative. Derivative, it is the limit of a difference quotient like such. Okay, this is difference quotient. It is always in the case as x approaching to 0, denominator 0. So even though in many cases we do have ways to calculate such a limit, but anyway, in general, you have to say it is not very convenient to calculate derivative using such a definition. So we are going to establish some rules. Really, the first rule, it is power rule. We'll talk about the power rule in a moment. And again, two more things I want to remind about derivative. Derivative, it is the instantaneous rate of change. This part, it is the rate of change, right? Because the limit, well, the rate of change in a very short time period. So that is the instantaneous rate of change. And then mathematically, if you are thinking about the graph, that instantaneous rate of change, indeed, it is the slope of the tangent line. And also another explanation of the instantaneous rate of change. The derivative of a position function, it is the instantaneous speed. It is the instantaneous speed. Okay. And also we mentioned that we do have high order derivatives. And at this time, I still just want to mention briefly when you consider second order derivative, and again, consider the function, it is for a position. Then the second order derivative, it is the acceleration. So that's for the reviewing part. And we said actually for this section, really, we are going to not going to stay with the definition forever. We want to move on. We want to see if we can establish some easier ways to calculate the derivative. And indeed, we do have some formulas and the rules. So really, the first formula or the first rule, it is called as the derivative power rule. To get a derivative power rule started, let's take a look at some of the calculations we did in the previous sections, like this one right here. F of x equals x squared, and I hope we still remember the derivative turned out to be 2x. And also, I believe we calculated a derivative of x cubed, and that turned to be 3x squared. And also, this might be a little weird, square root of x, but I hope you understand. In calculus, we always consider radicals, square root as x to the power 1/2. And indeed, we did get the derivative. Derivative is 1 over 2 times square root of x. And also, when you have square root of x in the denominator, I hope you see that really means x to the negative 1/2. So it is the same as 1/2 times x to the negative 1/2. The reason I'm considering those rational powers or negative powers because they will help to find out the derivative power rule. So in general, this is the derivative power rule, which says a derivative for any power function in the form of x to the power of r, x to the power of r. This is the power function I'm talking about. And then the derivative can be found by taking down the power of r as a coefficient for x. At the same time, decrease the power r by 1. You bring down r as a coefficient for x, then decrease the power r by 1. Okay. So I hope you see this really does match for those very simple examples, right? We bring down this 2 and 2 decreased by 1, that's 2x. Bring down this 3 decreased by 1, that's 2, that's a 3x squared. And also keep in mind the power rule, indeed, it is very powerful. And it works for integer powers and rational powers. When r square root of x is really can be considered as a power function, x to the 1/2, right? And then bring down this 1/2 as the coefficient, decrease 1/2 by 1. That's a negative 1/2. Okay. 1/2 minus 1. It is negative 1/2. So it doesn't match. And I have a few more examples, like derivative of x to the power of 10. Bring down this 10 as the coefficient for x. At the same time, decrease this 10 by 1. Still keep that as a power. 10 times x to the 9. And another weird power function, x to the power of 87. That is 87 times x to the 6. Okay. Some other examples. I'm talking about a derivative power rule. Keep in mind, the power for a power function could be of any real numbers, or could be of any real numbers. Okay. So far, we just covered something, well, integers, positive integers. And also, we did cover special case 1/2, a rational number. And they need this R, the power rule, the power of R could be of any real numbers. So the next example, be very careful. I am considering the derivative of 1 over x squared. And you really don't want to jump to the denominator to calculate derivative, say that is 1 over 2x. Certainly it is not correct at all, because we just introduced the power rule. So the only way, keep in mind at this moment, to find out derivative, it is to use the power rule. So I considered 1 over x squared as x to the negative 2. Okay, r is negative 2. Bring down this r as a coefficient to the front, negative 2. At the same time, decrease this negative 2 by 1. Negative 2 minus 1, that's x to the negative 3. So that is negative 2 times x to the negative 3, and that is the derivative. And also, it is very helpful. Think about case. If I ask you suddenly, what is 2 to the power negative 3? And even you ask for me, I guess, it takes 1 or 2, at least 1 or 2 seconds, I guess, or maybe 1 or 2 minutes to think about those negative powers. So I'm saying it is very helpful if you have a negative power and if you can convert it back to a positive power. Certainly in this case, negative 2 times x to the negative 3 would be x to the 3 in the denominator. By the way, I think I can make a change up correction here. This should be 2 and negative 2. I got the minus sign in the front, so the numerator still stays at 2 here. Okay. And this is a very important thing, the power rule. Certainly, I guess we have no problem to handle x squared, x cubed, x to the 10, x to the 100, those things. But make sure you do handle when sometimes you may have x squared, x cubed in the denominator. Okay. So this is the case how I did for x squared in the denominator. It is really considered as x to the negative 2. Then we use the power rule. The next example turns out to be very similar. 1 over x. 1 over x should be considered as x to the negative 1 power function. Because really, so far for now, the only rule we have, it is a power rule. So regardless, other than definition, for any function, you will have to consider to use the power rule. 1 over x, it is considered as x to the negative 1. And then the power, bring down this power, decrease negative 1 by 1. And also, as I just said a moment ago, if you can convert this negative power back to the positive power. So the answer is negative 1 over x squared. How about the square root of x again? Square root of x, okay. Square root of x, and actually we did the calculation in the previous sections. We understand that the derivative would be 1 over 2 times square root of x. And also I said that it might be helpful if you can consider, well, this as a negative rational power, x to the negative 1/2. So this time, let's try to find out derivative using the power rule. Clearly, square root of x, it is the same as x to the 1/2. Then I bring out this 1/2 as the coefficient for x, decreases 1/2 by 1, which turns to be negative 1/2, which turns out to be, actually this should be positive. I'm sorry, I need to make another correction here. It is just 1/2 times square root of x. To the 1/2, it is square root of x. To the negative 1/2 means square root of x in the denominator. Okay. And the last two examples might be a little more complicated. What would happen if we want to handle the derivative of 1/square root of x? Well, first of all, starting from square root of x in the denominator, that's x to the 1/2. But anyway, the entire thing in the denominator, 1/x to the 1/2, which is the same as for a power function, x to the negative 1/2. And this time, keep in mind, again and again, we are just doing the power rule. We bring down the power of r, negative 1/2, as a coefficient for x. Then at the same time, decrease this negative 1/2 by 1. That's a negative 3/2. So it turns out to be negative 1/x to the 3/2 in the denominator. And also, I'm going to leave that to you to see if you are convinced. X to the 3/2, indeed it is x times square root of x. Okay. And before we take a break, let me just finish one more example. Derivative of the third root of x. So accordingly, it should be considered a power function, x to the 1/3. Then I bring down this 1/3 as a coefficient, decrease 1/3 by 1. 1/3 minus 1, that's negative 2/3. And also, as I'm saying, it's very hard to understand a negative rational power. So convert back into somewhat a common form. The 3 stays in the denominator. To the negative power, which means the entire thing in the denominator. So I'm considering x to the 2/3 in the denominator. The denominator of the power converts to the radical index. 3, denominator 3 as a power. It is the third root. And this 2 still stays as a power. So overall, I'm having 1/3 times the third root of x squared. That's all about the power rule. Power rule. I say the power rule, it is very powerful. Keep in mind, in order to apply the power rule, you need to have some very simple power functions. Okay. Like 1/x squared, you cannot, you simply not allowed to jump to the denominator, or simply it is not correct to jump into the denominator. You are going to convert this into a power function. Okay. For the square root of x, you're not allowed to jump inside the radical notation to get a derivative. You have to handle this entire thing as a power function. So square root of x, that's x to the 1/2. Power rule, the derivative power rule, it is the most commonly used derivative rule, and it is, can I say it is the most powerful rule, really. It is the most powerful derivative rule, okay. And also, I just want to mention there are some simple cases for the power rule. For example, derivative of x, and also maybe I just want to make sure you know, sometimes we do write in this fashion. This is really dx over dx. dd notation, it is for the derivative. So it is 1, right? It is just 1. Because if you think about the power rule, this is x to the 1. Bring down this 1, then decrease 1 by 1, this is x to the 0. So overall, the result, it is 1. Derivative of single x, it is 1. And also, another special case, derivative of this 1. You can consider this a derivative of x to the 0. So you bring down this 0 as a coefficient, it will make the entire thing 0. Derivative of the single 1, it is 0. And also, we have somewhat a little more generalized conclusion. Derivative of any constant, it is 0. Think about it in this way. Derivative, it is about the rate of change. So when you have a constant function, the rate of change is 0 all the time. So derivative is 0. So this is the first part of derivative formulas and the rules. We have the power rule. Thank you for watching, and I'll see you next time.